so today I didn't.
You forgot to record. Oh, so, okay.
Yeah, I have put it on. Yeah, thanks. So I'll talk about immersions first. Okay, so well, the general sort of the theme would be immersions and embedding, and we'll be going towards the Whitney embedding theorem, which will be the kind of the first sort of non-trivial result, perhaps in the course. Okay, so so what's the definition? So last time we saw the definition of submersions. Maybe I should just sort of remind you a little, so last time we talked when sort of you have a map from smooth manifold to another smooth manifold. A smooth map, of course, is a submersion if, you know, sort of these derivatives at, I don't know, I guess I used a capital D. The derivatives at a point, so these guys are surjections, right? So it's surjective. Okay, and when it says submersion, it's surjective at every point x and m, right? So for all x and m. And now the sort of the definition today is when immersion is somehow sort of complementary to this, where assuming the level of derivatives that these linear maps are injective. Okay, so here I'm going to have the dimension of the source being less than the dimension of the target. So this opposite, or maybe less than or equal to, the opposite to what we had for submersions. So let me call it capital. So if then a smooth map f from m to n is an immersion if the derivative f of x n is injective at each x and m. And as before, I mean, immersion at a point x would mean that it's injective at that point x. Okay, so here, but without that, it just means that everywhere, right? And one sort of example is canonical immersion. Just like we had a canonical submersion, which was somehow the simplest example of a, sorry, I should say immersion here. So canonical submersion we saw last time. Canonical immersion is also something very simple. So here, remember your source is less than or equal to the target now. And a canonical immersion just means A1 to AK going to A1 to AK followed with zeros. Okay, so it's including in sort of somehow the sort of the perhaps the picture you can have in mind is, so now let's say the R2 mapping inside R3 and sort of is mapping into this plane, right? Perhaps. Okay, so this is somehow the sort of the picture, right? So the rest of the coordinates are 0, right here. Okay, so that's a canonical immersion, and the theorem here is just like for submersions. Any immersion is locally it looks like a canonical immersion. Okay, so this is sometimes also known as the local immersion theorem. So suppose fm to n, so suppose f from m to m is an immersion at a point x, and let's say y is f of x, then there exists local coordinates around x and y such that f of x1 to xk. So here this manifold is of dimension k, and the target manifold is dimension L. Okay, and L is greater than or equal to k, right? So then this equals x1 to xk, and if it's bigger, you fill out the rest to 0. So that's the canonical immersion. So this is exactly the analog of that theorem about submersions locally looking like a canonical submersion. This is the analog in the case of immersions. Okay, and some other picture. Well, okay, so we'll draw the diagrams in a little bit, but so what's the proof? Well, initially, so what's the diagram? You kind of start off with, oops, again, I keep mixing my notation here. So these are M and N. Those are the manifolds. And initially, you have these charts, or I should call them parameterizations, inverses of the charts, U and V, phi and psi. And these are mapping to neighborhoods of these points X and Y that we are focusing on, right? And so at the level of charts, you have a map G, right? So and here as before, so let me just say this is something we've kind of seen this diagram last time. We have a diagram of maps as on the right. Oh, sorry, on the left, and also sort of here we are kind of assuming phi of 0. So these are open sets in Rk and Rl respectively, and some of the map takes 0 to x, and this map on the other side, this parameterization, sorry, takes 0 to y. Okay, so somehow these are centered at those points of interest in M and N. All right, and what we know, well, we know that this the derivative of f is injective, and what it means is that this map at the level of charts G, so let me just say dx at f is injective, and this sort of implies that this map at the derivative at 0, this now it goes from Rk to Rl. That's the tangent space at the point in Rk at the point 0. So this is sort of, maybe I should use a different color. This is T0 Rk, this is T0 Rl, right? So this x goes to y, so the 0 maps to 0. The G takes 0 to 0, right? So anyway, so these are the two tangent spaces, and you talk of the derivative at the level of charts. This is injective. Okay, so this is what injectivity really means. Okay, this we saw before that we can go back and forth between talking of tangent spaces and points in the manifold, and tangent spaces, via a chart, tangent spaces on points in the Euclidean space. This is because these are isomorphic to each other, etc., etc. So this is where these local coordinates are useful. So because now it becomes like a multivariable calculus setting, right? So in particular, so this is injective, means that you can actually sort of again as before, so by rearranging the sort of permuting, let me just say, permuting the coordinates, we can assume without loss of generality well, actually, in this case, we don't even need to do that. So let me just say that, so this just means that a D0G looks something like this. It's remember, K is less than L, so it's going to look like there will be a square matrix here of size K by K, and then there will be some things here, and the point is that this will be something here, and the point is that this will be invertible, right? So it's sort of yeah, I guess maybe you do need to. I'm going to permute my coordinates so that the matrix, the derivative is of this form. So so without loss of generality, the bracket by permuting the permutation of the coordinates, which you can do. That's a linear change in, you're sort of, it's sort of a diffeomorphism of RK to RK, if you like, that you're precomposing with. So you can assume that the derivatives of this form, and in fact, you can also assume that it is, that invertible matrix is actually the identity map here. I mean, the identity matrix here, but maybe let me avoid that. I mean, you can just do that by post-composing. I mean, so let me just say that. So by post-composing or pre-composing by, maybe let's just say another linear change by I mean, you can do either, I suppose. But let me just say pre-composing by another linear map can assume that that this is identity. This is the identity matrix. Okay, but we won't quite need that, I think. All right. In any case, so so we have this map, and we want to. I mean, so the whole point is that we want to use the inverse function theorem, like, right? So want to use the inverse function theorem. Okay. So what you can do is so you have to get the dimensions on both sides to match first of all. So you define, instead of this map little g, which goes from something of lesser dimension to something of greater dimension. So you define capital G on some Euclidean space to RL. So where we've kind of, I've now increased the dimension of the domain, right, by this taking this product with R of L minus K. So now that the dimensions on both sides, this U was, remember, was subset of RK. Okay, so now these both are same dimension. Now, how do we define this G? Well, it's going to take, suppose you have a vector U, vector X in U, and Z in RK minus RL minus K. You define this to be little g of X, where G is defined on U, right? So so this G of X plus 0, 0, 0. I'll just write it as 0, comma Z. Okay, so this is sort of, so you fill in, so the first K entries with zeros, and then it's the identity map on the rest of the variables. Okay, so this addition is just the usual addition in RL. Okay, so you're adding to sort of vectors in RL, sort of the entries get added. Okay, and now if you compute the derivative of this guy now, so then sort of D0G would actually be an invertible map. Okay, so if this was actually, so if this was the identity map, if we had assumed this is the identity map, this will be the identity map here. So it's actually the, so let me write that in red, is the identity map, which is it's an L by L identity map. And if not, then it has some form that you can probably sort of figure out. It will maybe it is Yeah, actually, so let's see. So yeah, I think by precomposing with a linear map, maybe it's best to use that fact. You can actually sort of assume that this is the identity map and this is 0. Okay, so this is sort of the 0 matrix. So let me assume that you can do that. Okay, so this is, anyway, so this is some, without loss of generality, you can sort of, by precomposing, I mean, so somehow, so this, instead of this G going from U to V, this is in RK, you replace this U with something else, right? So you kind of have a diffeomorphism to U prime by a linear map that is defined whole of RK, so that this U prime to G. Now this composition, has this desired form. Okay, so this is what's, what I mean by without loss of generality. And you can also, permute the coordinates when you do this, so that it's the first k terms that becomes the identity matrix, and then the rest are 0. Okay, so it's the 0 matrix down here. Okay, but in any case, so once you have this and you're plugging in the rest of the rest of the map is just is basically the identity map on the rest of the L minus k variables, right? And so when you do that, you'll actually sort of you're basically going to add in an identity component over here and make this matrix bigger with the 0, 0, and then this identity on L minus k times L minus k, and you'll get the identity matrix of size L. Okay, so L by L identity matrix. Okay, and now that you've gotten something which has an invertible derivative at the point 0, you know by the inverse function theorem. So by the inverse function theorem, G is a local diffeomorphism. Okay, so at 0. Okay, so and this 0 is an RL, right? So this is 0 in RL. So from RL to RL, it's a local diffeomorphism. And note that the way I've constructed it, that G, that little g is just capital G composed, well, precomposed with the canonical immersion. Okay, so if I do a canonical immersion from RK to RL, so remember this x1 goes to x1 to xk, goes to x1 to xk, followed with some bunch of zeros, perhaps, right? And then you apply G, then you'll be basically just, now you'll be going to, so RL, this G is from RL to RL, but what you'll be doing is you'll be going to G of x, right? G of x1 to xk, right? Because this term, this addition of 0 and z will be, this will contribute nothing, because these entries, this L minus k entries, are all 0. Okay, so you can write G as a composition of this and this canonical immersion, but the point is that if you restrict, so G is a local diffeomorphism, so there's a G inverse that exists on some suitable open neighborhood, open set around that contains 0, right? So we can, so what we can do is, so we can write, we can change our so our chart that we had, so sort of somehow the we kind of sort of get, sort of we can have this chart instead. So this will be something like this. So we'll keep this the same, and we can change. So this was originally, this was psi going to V, but now and this was G, but we are going to change it to, this is the canonical immersion to some V prime, and here I'll do G. So this V prime is chosen so that so there is a there is a G inverse from V. Well, I guess, right. So what's going on here? So maybe I should. I mean, we can assume that V is chosen so that this G is a diffeomorphism. Well, the G inverse exists on V, and then you kind of choose your V prime to be the pre-image, so to be G inverse of V, so something like this, right? So you can kind of sort of shrink. Let me just mention that you can shrink U and V such that the diagram on the left makes sense. So you choose it so that, because all that we know is it's a local diffeomorphism. We don't know at where exactly it's a diffeomorphism, but you just sort of sort of shrink your U and V so that G is actually a diffeomorphism there. So then you can talk of G inverse, and now this G inverse will take you to some other subset of RL, and so this guy is sitting inside RL. This is an RK, but now the point is that this composition now V prime to N is going to be a new parameterization, and the local expression for F, if you take the phi and this, is just this, which is a canonical immersion. Okay, so so now somehow, let me just redraw this. This is just M to N, this is phi, this is psi composed with G, and I've shrunk U and V so that this now is a canonical immersion. So this is a canonical immersion. So I've changed my charts. All that we needed is some charts in which F looks, some local coordinates in which F looks like a canonical immersion, and that's what we've got. Okay, so we started off with some random local coordinates, but all that we knew was that this derivative is injective, but then we can do this local change using the inverse function theorem and get to some chart where you have the local immersion, right? Anyway, so locally, whenever you have an immersion, your picture really looks like I drew here at the very beginning. Okay, so where you have this the plane. So here maybe I should have drawn should have shaded the plane to sort of this is the plane. R2 is mapping in to this something sitting inside R3. So this is an example of R2 immersing in R3, right? And so somehow locally, whenever you have an immersion between smooth manifolds, this is the picture. Okay. By the way, a consequence of all of this discussion, both for submersion and immersion, remember there's a case when these are okay. I'll update the notes. There's a case when equality holds, right? And so if you think about what happens to both of these cases when equality holds, you'll see that it just means that locally you are a diffeomorphism, right? So if your derivative is an isomorphism at the level of tangent spaces, then locally you're diffeomorphism. So somebody had asked this when we saw one implication of sort of one side, one direction of this earlier, whether the converse is true. So these theorems tell you that indeed the converse is true, right? So this sort of it's basically the inverse function theorem, applying that at the level of charts. Okay, so I hope that made sense. I mean, so if you were the one who asked the question earlier, it would make sense to you. Anyway, so now that we know what an immersion is, let's sort of see some more examples perhaps. And there's one, important thing that one should keep in mind when talking about immersions. The fact that yes, yeah.
Yes, sir. In the case of submersion, we saw that
Yeah.
the inverse image of a point gives us a submanifold with some
Right.
condition. I mean, under some condition. In this case, shell injection from a subset of the manifold to the manifold will give us a submanifold if this injection is this immersion.
Yeah, that's exactly what I'm coming to. That's a good point, right? So in this, that's what the next question is. So for example, here what is happening is when I'm immersing R2 inside R3 and it's sitting as a plane, and that plane is a submanifold of R3, right? So one can ask whether if you take an immersion from a lower dimensional manifold to a higher dimensional manifold, then is the image of the immersion a submanifold? And that's exactly what I'm going to now say is this note. Note the image of an immersion, it need not be a submanifold. So need not be a submanifold. And let me give you two sort of examples where it is not a submanifold. Okay, so example one is suppose that in my manifold M, the domain manifold is a circle. Okay, it's S1. Okay, so here sort of M is going to be S1, and the target manifold, which has to be bigger dimensions, R2. Okay, so you can do an immersion as follows. So what you can do is you can have a map. Let's say it starts at some point, it maps it there, and then you kind of traverse the circle, and let's say in the counterclockwise direction. And while traversing, you traverse in the target. Your image traverses like this and becomes a figure 8, and you come back and then you kind of repeat yourself. Okay, so this is an example of a map from S1 to R2. I mean, I'm sure you can write down an explicit such map which does something like this. Okay, and it's going to be an immersion because after all, what does it mean for something to be an immersion from when your domain is a circle or let's say one-dimensional? It just means that whenever you have it just means that sort of some non-trivial sort of tangent vector goes to non-trivial tangent vector here, sort of the level of, I mean, so if you yeah, so anyway, so it's sort of I guess I didn't talk about the sort of the way that one of your homework problems is about thinking about what tangent spaces also are. I mean, but I'm sure that you're familiar with the concept of tangent spaces as sort of as some kind of supporting lines or something. So right, so if you're looking at a tangent vector, so then this vector sort of goes somewhere. So it's a non-trivial vector, and sort of you can see, if you write down this map, you can, as you progress along this circle, you're making definite progress along this figure 8. So you're sort of non-trivial.
Is it?
Yeah, you can think about that. Yeah, right, exactly. Thanks. That's another way of thinking about it. So velocity of your thing is non-zero, so that's an immersion in this case, where your domain is just a one-dimensional, sort of a manifold. Okay, so one-dimensional manifolds are just basically circles or lines, right? anyway, so this is an example of an immersion, and the image is not a manifold, right? So let me just remove these orange thingies. So the image is this figure 8, and it's not a manifold here. So it's sort of it's not a manifold around this point, right? And on this point, a manifold should, if it's a one-dimensional, sorry, it's not a, what do I, maybe I should say it's not a submanifold. Not a submanifold. So for a submanifold, remember you can straighten out. So submanifold is something where you can straighten out to look like a slice, right? So if you something which is a manifold is something which maybe looks something like this slice, right? So you have a point and you have a slice. So this orange part is a submanifold, okay? But here you don't see this picture. I mean, you can prove it in various ways. I mean, this subset is not locally Euclidean at that point in the center, right? So you don't have a neighborhood in which it is an interval, right? Anyway, so this is not a submanifold. So this is an example, and so let me give you another example before talking more about example 1. So example 2, this time your M is R1, so it's still a simple kind of thing, and N is R2. Okay, so and N is R2. Okay, and what you can do is you can map the real line. Well, it sort of goes on in both ends. So that's your R. You can map it in so that again the image is going to be a figure 8. So it's sort of mapping it like this, and maybe sort of this part. So these dotted ends sort of are going towards that central dot here. So maybe the central dot is the image of 0, and on one end of it, it goes along this, let's say you on the left-hand side, you start with the central with 0, and then you go on the right a little bit. So here you'll be going along here, and then sort of continuing and approaching but never reaching this point. Okay, so all right, and then if you go left, you kind of go around here, and then as you keep going left, more and more negative, then your images goes towards but never reaches this dot. Okay, but the image is still this figure 8, right? If you think about it, right? So this is again not a submanifold. So these are sort of not a submanifold. Let me just write it in red so that it's prominent. It's not a submanifold. Image is not a submanifold. Okay. Right, and here's another example. Let me here's a slightly more complicated example. So here's what you can do. So here, the M is going to be R1, and N is S1 cross S1. All right, so S1 cross S1 is actually a surface that is familiar to as a manifold. It's a two-dimensional manifold, so it's a surface, and I guess you all know that it's a torus, right? So it's a familiar surface to you. It can be you can visualize it as in R3, right? But you can also, obtain it as a quotient of R2, quotiented with Z2, right? So this additive subgroup of integers, if you think of R2. So R2 is this is actually an example, and we'll probably see more of that later on. So quotients of Lie groups, right? So R2 is this manifold, but it also has this additive group structure. So it's a Lie group. This we've already seen. So you can actually quotient it with some subgroup, Okay, here the subgroup is this subgroup Z2, so of integer lattice. Okay, so so when you do this quotient, sort of you get a torus. This is something that you've probably seen already. But in any case, what you can do is you can have a map which is an immersion from R to S1 cross S1 by first sort of putting R in R2, and then sort of this is the quotient map. This is sort of the pi is kind of this. We think of it as R2 quotient with Z2. You think of so F. Our immersion is going to be pi composed with F. All right, and what's this F? Well, capital F is just also so this line embedding. Well, so I didn't talk about embeddings, but this is a straight line of irrational slope. So suppose this is the origin. You kind of pick some line. So this is the image of F. So it's a line of irrational slope. Okay, and so it is. It's a fact, and I'm sure you can sort of prove it that if you have a rational slope, then on the torus you'll close up. You'll kind of go around, and then you'll close up. It's like sort of on this grid. Let's say if you have rational slope, if you start at, let's say, 0, 0, you'll end up at some mn, right? So one of these grids. So these points, they correspond to the same point in the quotient, right? So what will happen is that you'll be sort of looping. You'll be closing up this line segment under this quotient will map to some closed curve, right? And as you progress, you'll be just sort of traversing the same closed curve again and again. But if you're irrational like this, then if you start off somewhere on the torus, you kind of never close up. You kind of keep going, and you actually sort of never intersect yourself also, right? So it just keeps going, and it keeps filling up, anyway, so and then you get something which is dense on the torus. Okay, so this the sort of this will give you this is an immersion. So this let me just sort of conclusion of this example. So this is an immersion that so whose image. It's also an immersion, by the way, because sort of again you'll be going along constant velocity, perhaps along all of these, but at least non-zero velocities. There's an immersion whose image is dense in S1 cross S1. So in particular, it's not a manifold also. Okay, but it's not a manifold. But is not a manifold. Let me just say that. I guess you could have something which is dense and a submanifold, but here, so I should say submanifold. It's not a submanifold. Why? Because sort of locally, if you look, sort of around a point on this image, then you'll be traversing this part many times, infinitely many times. You'll be sort of you're never going to get a picture where you're just a slice. That's what a submanifold is. A submanifold is every point you look around it. There's a neighborhood in which sort of up to some change of coordinates, your subset looks straight like a slice. Okay, so somehow sort of this doesn't happen. Okay, so this does not happen. And what happens is this picture which I've tried to draw over here, it's something which is sort of these images when you kind of go around. I mean, sort of this irrational slope that they are getting dense and sort of they're filling, sort of things are getting closer and closer. They're not quite sort of filling things up, but it's getting dense. Okay, all right. So anyway, so this is another example. All right. So what is going wrong in these examples? So the first one is sort of easy to figure out what is getting wrong. Well, it's just that this map F that we had, so I didn't name it, so this is our map F. The map F that we had is not injective, right? So that was one of the problem, right? So if sort of this part was kind of going out, coming back, and then hitting itself. All right. So when you have such a thing like this, then at the point where it is hitting itself, then around it, it will not be a manifold. It will have this kind of figured eight sort of behavior. All right. So this was the problem here. The problem with examples 2 and 3 is slightly more. It's not that it's not injective, right? So because the maps we constructed were injective. This was our F over here. This F also is actually, one can show, is injective, but there those that something else that goes wrong is. So yes, somebody, yeah.
You are not audible. Your voice is breaking.
I'm not.
I mean, it's, at least for me.
Okay, so now is it fine? Yeah, sometimes the internet is not always that great. That's one of the reasons why I turn off my video. Okay, because the connection here is not always that great. Anyway, so all right, so so the definition is an immersion. So this is an immersion that is going to be a good immersion in some sense. It's an immersion that is injective. Okay, this is one good property, and is called an embedding. Okay, so this is finally we get to what an embedding is. Okay, and to smooth manifolds, to any spaces is proper if pre-image of compact sets are compact. It's compact whenever K is compact. Okay, this is not true for our examples 2 and 3. Okay, so for example, in example 2, if I take some neighborhood, let's go of this central point, right? That's a let's take a closed neighborhood. Sorry, let me take a closed ball. I want a compact neighborhood, so maybe I should have a different color. Anyway, so this orange thing, let's imagine this is a compact set. Maybe I should draw the boundary of that set also. Okay, so somehow this is it's a closed ball. All right. But what is its pre-image? Well, its pre-image under F is going to contains some of these ends, right? Parts of these ends, because these are the ones that are approaching this point as as you go sort of, well, as you go in the left and right, the positive and negative ends, your image of F will eventually map inside this compact set, right? So the pre-image of this compact set are not compact. It's sort of, so this map is not proper. Okay, and you can also sort of similarly see that this irrational slope curve and on the torus that's sort of becoming dense is not going to be a proper map from R to the torus. anyway, so if a map is injective and proper, sorry, if an immersion is injective and proper, then it's an embedding, and that's the definition. And actually, so the theorem is that these are properties that would guarantee that the image is a submanifold. So an embedding from f of m to n. Let me sort of call it x and y, because sort of some sort of sketch of some notes here, which where I use that. Okay, so here these are smooth manifolds. X and y is a diffeomorphism to a submanifold of y. So that, in other words, its image is a submanifold. Okay, so when you have an embedding, its image is a submanifold. Okay, so this is this is one good thing about embeddings. That's why we we look for things which are embeddings when we try to think of immersions and so on. Anyway, so well, what's the proof of this? So I won't get into too many details here. So essentially, I mean, so it's you can show that. So after all, so what is it? It's so what do you mean? It's a diffeomorphism to a submanifold. So basically, so what am I trying to show? So the x to f of x sitting inside y. So I want to show that sort of this map. So let me just write it here. So this f, I want to show that this is a diffeomorphism, right? So we already know that this is injective, because an embedding is always injective, right? And we also know that, so we know that it is an injective map. We also know that it's a surjective map, because we are just looking at the image of the domain. So that's surjective. We also know that. So what else do we know? We know that. So it's an immersion. So this is so. We kind of so we know that f is smooth. This we know. So we want to show we want to show that f inverse is smooth. Okay, this is what we really want, right? So and you would think that, oh, sort of f is an immersion, right? So once you are an immersion, then you can basically sort of use the so we also know that immersions locally look like a canonical immersion, right? So once you look like a canonical immersion, then you should be done, right? Except that you have to so it's almost true. So you have to check that sort of neighborhoods of points in the target sort of look like, so your target looks like a slice in the bigger manifold Y, right? So remember, you want to show it's a submanifold. So a priori, you don't know that, right? So one of the, anyway, so let me just say this, and sort of I leave you to kind of sort of convince yourself that this is really enough. I claim that it's enough to show that if W, that this is an open map. So if W in X is open, then the image of W, this is an open subset of f of X. Okay, so right, so this wasn't quite true in examples 2 and 3. You can try to sort of figure that out. But once you know this, once you know that f of W is an open subset of f of X, then basically so you can choose your local coordinates. In the local immersion theorem, you can choose your local coordinates to lie inside this f of w on the target, and inside this w in the domain, and then you know that locally your target is so on those coordinate charts your map f looks like a canonical immersion, and so therefore you know they would conclude that in this f of w, or the smaller neighborhood that you chose in there, your image will look like a slice. Okay, so so we kind of, so it's, if we can show this, then we are basically done. So we kind of can show by using the local immersion theorem that your image is going to look like, you know, slices and appropriate coordinates chosen inside this open subset. But if this thing is not open, then you are in trouble, right? So then you can't really choose those local coordinates nicely enough so that you know that it's a submanifold. Anyway, so this is enough to show this. So that's what we can show. So what do you do? So so here's the argument. This is now just, you know, just point set topology, right? So so if not, suppose it's not an open subset, so then there exists a sequence, let's call it yi, in the complement f of x minus f of w, such that yi's converge to y, which is an f of w. Okay, so this is just something, some subset not being open means that you can approach it from the complement, right? So and so so if this is a convergent sequence here, so this is yi's converge to y, and so you can say that the subset of all the yi's together with y is compact. Okay, so that's my K. Okay, that's my compact set in. So this is going to be a compact set in Y. Okay, so compact. Okay, so in Y. All right, and so therefore, if you take its pre-image, so let me just say, so let's take its pre-image first. So let F inverse F is injective anyway, so you can define a pre-image of these guys in X. Okay, Xi's and X. So now by the properness assumption, so since F is an embedding, it's also proper. So we know that this subset Xi's union X, this is compact, because pre-images of compact sets are compact. That's proper. All right. So and so by passing through a subsequence, your Xi's will converge to some Z. All right. So these Xi's is it's infinitely many points in some compact set. Right. So and by the way, these are not just arbitrary topological spaces; these are manifolds, right? So they have all these other, you know, equivalent definitions of compactness, like you know, infinite subset has a limit point, etc. These all hold true in manifolds. Maybe it's, you know, not for arbitrary topological spaces. Sometimes there are distinctions, but those don't affect us in any way. All right, so this happens because of the compactness of this pre-image, and so so just by continuity of f of x will converge to f of z, right? But since we already know f of x is yi's, and yi's converge to f of z, and yi's converge to x. So y by assumption. So we already know that f of z must be y. And so by injectivity of f, we know that x equals y, right? So because we have f of x going to y, something we saw before, and we also have f of z equals y. So since f is injective, sorry, x must equal z, sorry, not x equal to y, x equals z, right? So so in fact, so f of xi's are converging to which are yi's, are converging to well, so let me see. So yeah, so right. So z equals x, but what's a contradiction now? Well, so right. So by assumption, so these guys, I forgot to kind of mention it here. These xi's belong to w, right? So sorry, so not xi's. This right. So y. Sorry, this x belongs to w, right, by assumption, right? So
Prediction is W is not open, I guess.
yeah, that's right. Yeah, so these, yeah, so now coming back to, so we have xi's converge to x, and x belongs to w, right, by assumption, because y we chose to be something in f of w, right, and x was something that was mapping to y under f. All right, so in any case, so this goes to w, but w was open, right? So this was open. So this means that xi belongs to w, you know, for all i's sufficiently large, right? That's the only way you can approach some point in an open set. And this contradicts the assumption that yi's are not in f of w. Okay, so the xi's we chose are the pre-image of yi's, but yi's were not in f of w, so it can't, xi's cannot be in w. All right, anyway, so this is sort of some point set topology that comes into play here, and once you know that this image of open sets is open, this map is open, it's easy to kind of do the rest and to use the local immersion theorem to say that this image is a submanifold, okay, and this f is a diffeomorphism from x to that submanifold. Okay, so that's an embedding, and so next time we'll talk about the Whitney embedding theorem, okay, which embeds manifolds inside Euclidean space. All right, so anyway, so next Monday we'll meet next Monday. Sorry for going over time. So now I guess maybe some of you were wanting to listen to that seminar. I should hurry there too. So see you next Monday, and I'll take any questions you have then. Okay, so or you can always, of course, email me if you have questions. Right? So I'll update the notes. Any quick questions, by the way? I hope this was understandable to all of you.
One question. So if you don't have